Thank you very much for the invitation. That I must say also that I really appreciate it. I followed Alex Wendt's work over the years, and especially the book Quantum Mind and Social Science. I think it's an absolute Bible for the field in the way that it really covers these different areas of applying quantum theory, not of course social sciences, but also in philosophy and other areas. So it's really, I always feel that the fact that that there are some references to my work means at least that the author has done very thorough work, because there are other approaches that are much more visible, like the Penrose-Hameroff approach, and then some of us perhaps we publish in more, even some fringe journals or conference proceedings and things like that, so. But anyway, I really think there's much there, and I even feel there, for example, I think what Alex says about perception in the book is still extremely interesting. I'm very tempted to that one could maybe do something interesting there, but that'll be in another occasion. But okay, so I thought of today talking about this kind of the base of the work of David Bohm that I'm familiar with, and of course then with some of these ideas I've also worked with Basil Hiley, who used to work with 30 years with Bohm. So Basil and I have kind of interacted with another 30 years. So you can imagine Basil goes 60 years, still very active, and we had just a little meeting in Sweden focusing on Basil Hiley's work just last week. I'm just back actually yesterday from Sweden. Anyway, but here I'm setting this up in a philosophical framework. Those of you who have a philosophy background will know what I'm talking about here when I say interactions, dual aspect monism. You might even be a little bit puzzled. This is like an oxymoron, because isn't monism means that you have just one thing, and okay, you can have a dual aspect monism, but what is this interactionist business doing here? Because usually we think interactionist has to do with dualism, Descartes, where we say that we have dualism, we have two substances, consciousness and matter, and they interact. But of course, then people say, well, Descartes could never show how they do that. And the way I'm thinking of the Bohmian scheme is that it's an underlying monistic framework where we still say that mind and, or if you like, matter and consciousness are different from each other. But still, in some ways, they are, rather than being separate substances, they are some sort of aspects. And the question is whether aspects like that could influence each other, perhaps that we might even use something like the word interaction there. But this is, if you like, my long term, because I've been doing these things for, I don't know what, 30, 40 years. So it's kind of trying to just describe what I would like to have as a philosophical view. And so the anyway, in this slide you can see the way one thinks about here is that we say that reality has manifest levels and then subtle levels, where we call the manifest physical and the subtle ones mental. And so but these, so there are levels of one reality. They still can influence each other. And the new idea here is that information would act as a bridge between the levels at this stage. And now, of course, we have to be careful. What do we mean by information in this picture? And I'll try to describe that as we go along. But anyway, so perhaps, I don't know, somewhat tongue in cheek, we might say that we are here dealing with the missing link between mind and matter, or perhaps even, there's the famous explanatory gap between matter and consciousness. So could information be the bridge over that gap? Okay. And so Now you might, of course, you could say, well, why would we want to have such a view? Why yet another view for this mind-matter relation, which of course you see would be in a way important for social science, because you might say that even for social science the question of you know, the mental and the physical is important, and it will in various situations be relevant. And here is just on the yellow, I've just listed some views that you are there in the philosophical. I mean, some there in the tradition, like Cartesian view would be the interaction substance dualism. There's something when people don't want to say that consciousness is a separate substance. They might say that we have something like mental properties. They could be properties of the physical domain. But one trouble there is then that they seem to have left causally inefficacious. Physicalism is this overall, some would say that it's a very common in philosophy of mind today, but some criticism is there that if you look at the philosophical literature of physicalism, they typically don't discuss things like quantum theory and relativity. And so what they do have is what we could call a very old-fashioned a mechanical view of the physical world. The philosophers Ladyman and Ross call this A-level chemistry, the level at which philosophers discuss the physical world. And of course, then what you see, the idea here is that if we want to be a physicalist, then we should also take into account our best theories of physics. One view that is very popular, of course, these days is idealism. There are, people like maybe Donald Hoffman, Bernard Kastrup, and also in philosophy, people like David Chalmers discuss it. But I would say still that if we take idealism, it cannot do justice to the obvious fact that the universe has a material aspect which exists independently of the human mind. And I put the obvious in square quotes because, of course, you can always, defend idealism. But I mean, for me, this is partly just intuitions after many, many, many years. So although I can see that idealism is an attractive view, I still feel that it's too one-sided. Of course, then there are panpsychism has been a very popular also in philosophy. There are people like Galen Strawson, Philip Goff, also David Chalmers has written about it. But if you do a very the usual strong form of panpsychism, you typically say that even elementary particles are conscious. And I mean, I have been flirting with that kind of idea, but still, I think that's a little bit too strong. So I would be happy to say that maybe they have some kind of proto-mental or even proto-conscious properties, but perhaps not all the way conscious, that it gets an implausible view. Now, then there's philosophy of mind, there's functionalism, which is more focusing just that when we talk about any mental state or conscious state, what's interesting is the role, if you like, a causal role it plays for the organism. And that is, of course, a kind of fairly neutral view and interesting to think about. But what tends to happen in philosophy of mind that people combine that with this very usual mechanical physicalism, and then what is left out is the mind. So we don't have the qualia consciousness, things like that. And finally, one view that is also quite popular these days is illusionism, which suggests that at least some aspects of qualia, like this, what is it like to be feeling, or some aspects of consciousness, like qualia, or we have the sense that there's something it's like to be conscious, that they would be some kind of analogous illusions. So the illusion, and this goes back to Dennett and Keith Frankis, maybe Nicholas Humphrey at least earlier phase. And there again, I would say that just like with idealism, I would say that illusion denies the obvious fact that phenomenal properties exist. And as you see, this also shows you a little bit the situation in consciousness studies. That there's really a lot of disagreement. On the one hand, you have things like panpsychism is saying that everything is conscious, and on the other extreme, there's this whole view that maybe consciousness doesn't exist. At least, great parts of consciousness are just an illusion. So the field is really pretty diverse. And then, of course, what I'm trying to do here with this dualism monism is just, I don't know, it's maybe you could easily say, well, I'm trying to have my cake and eat it too, because I do want to acknowledge that conscious experiences are real. I do want to acknowledge there exists a material world independently of our consciousness. And I also hope, I'm asking, can we have a view where conscious experience and material world are aspects of a single universe, a single reality, and that we could even understand their relationship, like how consciousness can influence matter and vice versa, which seems to be what's going on. I mean, you you open your eyes and you will see experiences in your mind, or if you drink a little bit of beer, it'll change your state of consciousness. And at the same time, when you reflect, deliberate a lot in your mental, in your conscious thought, then that might, typically leads to action. So it seems obvious there's a kind of two-way traffic between the mental and physical, but it's just very difficult to make a theory about that. Anyway, so I'm going to focus on David Bohm, and he's, of course, long ago, Mario Bunge called Bohm the David who faced the Goliath of quantum indeterminacy. And this is because, as well, many of you, if you studied quantum mechanics or read about it, you may have picked up that somehow quantum mechanics gives indeterminism a very crucial role. And the fact is still that we cannot predict what an individual electron will do. And from that, people already in the 1920s, they assume that from the fact that we cannot predict, then they inferred that maybe there is no cause for what the object does, what the quantum object does, and therefore there will be some sort of genuine quantum indeterminacy, if you like, in the world, or ontologically, as we would say in philosophy. And what Bohm did in 1952, after discussions with Einstein, he showed that it is possible to provide a deterministic description. And so in that sense, this was kind of an important counterexample. But it's still a hypothesis, so it's not as if Bohm proved that there is no quantum indeterminacy, but he also showed that it could be, we have different options there regarding the question. And so what I thought here, I'll do a little bit, just a very quick tutorial. I don't know, I hope this is not too obvious for some of you, but I just thought that before I start talking about the Bohm theory, I just want to do a very little baby physics, if you like, so that you hopefully understand better. It's partly because I've noticed that even with my philosophy colleagues, sometimes I go too quickly, or I don't say some things, and then it seems that it's hard to understand. So we're just going to do a little. There's this famous two-slit experiment in quantum mechanics, and we're going to see how ordinary so-called classical waves behave there. They could be like water waves, but also light waves. And then ordinary particles like little bullets. And then number 3 will be quantum objects like electrons. So there are, and so let's first do the ordinary classical waves. And this is the thing with putting them through a slit is here when the slit is much larger than the wavelength, then nothing very interesting happens. There's a wave from coming from the left, going through the slit, and because the slit is so big, so the wavefront just keeps going. And I mean, you might see some little things on the edges, but still on the whole, nothing dramatic happens. Now, if you make the slit, there is actually a mistake there. It should be much smaller than a wavelength, or at least roughly the same size. Then what happens when the slit is small and the wavelength is the distance from this crests of these waves. We are looking at the waves from above. This could be water waves, okay? And you can see that the waves, when they go to the slit, they will bend. That's called diffraction. And then if you make two small slits, now you get two diffractive waves, and when they meet, they can interfere. So at some stages, depending on the phase of those waves, when you can get a big wave, but in other areas, you can actually, they cancel each other out, and you get no waves. And you see, the amazing thing is that you can even do this with light waves. And it means that when two light waves meet, you get darkness if those waves have the opposite phase. So that's quite magical if we think of ordinary intuitions, that this is the phenomenon of interference. That's very important in physics. And so here you can see this is an actual photograph of water waves in two slits. They're coming again from left toward the right, and they add up some directions and cancel in others. And here is this more schematically, and now you can see it on the screens. There's this pattern of there's this interference fringes, where you have some areas where you get waves and others where you get nothing. And so interference, we could say, is a signature of a wave. So when a physicist sees a pattern like the one on the screen, they immediately think we're dealing here with a wave phenomenon. And so anyway, now we come to look at how ordinary particles, little bullets, behave in the two-slit experiment. And here it's not, somebody's here shooting with this machine gun and shooting, so moving the gun a little bit so that but what happens is that you get two piles of bullets to the screen, and that's sort of not mysterious why that happens. That there are just those two holes are the possible places, so only particles that go to the holes get through and others are stopped, and then you get two piles of particles on the screen. So that's not very mysterious. What happens then with quantum objects like electrons? And you see, historically, the electron was initially assumed to be a particle because it has particle properties like mass and charge. So you somehow feel these are localized with the little entity. So, physicists would expect that it should behave like a little bullet. So this is how physicists expected the electrons ought to behave. But here comes the surprising thing. This is actually, when you do the experiment with, this is what the experiment shows. So we actually, you see, the picture is a little bit misleading because we don't actually observe the particles moving. This has to do with the Heisenberg uncertainty principle of quantum mechanics. But what we do observe is what you can see on the screen over here. This is what we observe. And you see, and of course, the first puzzlement is that the electrons can come one by one. Why do they? How come they make this many piles or many stripes rather than just two of them, right? This is the big mystery. And if you compare the previous pattern with this wave pattern, we can see that they are forming kind of an interference pattern. And so, but notice that we get an interference pattern even if the electrons enter the slit system one by one. So here are some photographs from the actual experiments they've done. So in the picture A, there are just 10 particles, and they come here they come kind of randomly, which is typical of quantum mechanics. So it looks like there's a statistical process here, but gradually they still build up an interference pattern. So it's not complete randomness. There is actually also, if people call this statistical causality, that one by one suddenly a pattern emerges. Here you can see here you can see the end result better. And so this the mathematics of quantum mechanics can predict this pattern very accurately, but it cannot tell where a single particle comes. So we cannot predict where a single we can only say where it doesn't come, and we can assign probabilities. So it's more likely to come in the middle, but still with the individual object, we cannot predict that. That's again, if you like, has to do with the uncertainty principle. But anyway, so what we're seeing here is what has been called the wave particle duality, in the sense that an individual system, it exhibits both particle properties. It would arrive at the detector at a single spot, and it also exhibits wave properties, because the place where the spot appears is constrained by the mathematics of wave behavior. Remember, I say that you can calculate from these mathematics of quantum mechanics the possible areas where it can come, and even assign probabilities. So somehow, and you could say, well, even the single individual particle must know about the wave mathematics, because otherwise, how else would it know? You see, as you can see, that the particles don't really go here into this area. So how does a single particle know that it's supposed to obey this, if you like, the possibilities allowed by the mathematics of waves, rather than the good old Newtonian physics where you have just two piles, okay? So that's why we say that even a single object has this wave property in some way. And you see, there is still no commonly accepted way to explain the two-slit experiment for electrons. There are a number of interpretations. There's the Copenhagen view, there are the pilot waves, there's many worlds, spontaneous collapse, cubism. I don't have to go through all of these, but you can read about them there are some good popular books and some philosophical writings as well. I'm going to focus, and here you can see more, this is from Wikipedia, where they listed these and classified these interpretations. So you can see here's the Copenhagen back in 27. This is the Broglie Bohm theory is 27, and then Bohm read it at 52. You have the many worlds interpretations, Hugh Everett. Today, for example, David Wallace has been writing about it a lot. There's the exotic view that consciousness causes collapse of wave function. David Chalmers, Kelly McQueen have been writing about that. Then there are various other ones. And there's also cubism, which says more that the mathematics of quantum mechanics is really describing our subjective probabilities by Christopher Folks. But I mean, again, just to show you that after like 100 years of quantum mechanics, there's still this kind of disagreement about what the theory means, and especially what, if anything, it tells us about reality. And so but I'm just going to look at one of them, namely the de Broglie Bohm theory. And one of the reasons, well, we really don't, we didn't know which interpretation is correct in any obvious way. If we did, I guess then people would accept it. But at least what we get from the Bohm theory is that it does provide an explanation of, for example, the two-slit experiment. And you see, we go back to the situation, what the de Broglie Bohm theory does, it says that the electron is a particle accompanied with a new type of quantum field which guides it, so the pilot wave. And so here you can see that it's not just the particles that are going through two slits. It's like each particle will go through one slit, the wave goes through both slits, and somehow the wave is able to tell the particle whether or not, two slits are open. Because if you would close one of the slits, you would not really get an interference pattern like that. So somehow the particle going from one slit has to know whether or not the other slit is open, and in this model, it's the pilot wave that's telling it. And so so here we go. This is more stating it again. What this in this interpretation, what you do, one assumes that an electron is a particle which has a well-defined position momentum at all times, and it's accompanied and guided by a field psi which satisfies the Schrödinger equation. So this is really coming from the Schrödinger equation. It's not adding things to it. That's a kind of, there are some misunderstandings of the Bohm theory. But anyway, so this is why the way one gets it, and notice again that we're assuming that there are particles. You see, this is, you might be puzzled if you haven't read much physics. You might think, oh, you know, there are surely the electron is a little thingy, it's a little particle there, the elementary particles that everybody's talking about. But in so-called standard quantum mechanics, the kind of quantum mechanics that people like Heisenberg, Niels Bohr set up in the 1920s, they did not assume that the electron is a little particle. They were just using this wave function to the object. And it was not quite clear what the nature of the system is. And therefore, in this model, you're just postulating the particle there. But also you're postulating the wave, you see. So that's how so you see, in this model, it's not particle or field, because when you read popular books, they will tell you that it's a field or wave when it moves, but then it's a particle in otherwise. There's the famous collapse of the wave function, okay? In this model, it's not a field which collapses into a particle. There's no collapse in this pilot wave. Although in some ways people can construct something that effectively looks like it, but strictly speaking, because there's the particle, you do not need to assume a collapse to explain why you see a particle. Again, in this model, it's not a field which branches into many worlds. You see, again, in the by assuming the particle, we can understand why we have just one world, because the world where we are is made of these particles. And one of the motivations of introducing the idea of many worlds was to avoid the notion of collapse of the wave function. But in this case, we say that it's a single electron is a particle and field, or as Bohm put it, it's this kind of union of them. And you see, well, again, in the usual interpretation of quantum mechanics would say that the wave function does not describe an individual quantum system directly, but it would describe our knowledge of the quantum system, typically in terms of probabilities. But in this Bohm-Hailey picture, BH means Bohm and Hailey version, is that this psi describes an objectively real field guiding a particle such as an electron. And we can also use the wave function to calculate probabilities, but you know, the stronger interpretation is to think of it as really in a realist way. And this is a more technical slide. This is made by Hailey, and it just shows how you work it out. So the trick here, which a lot of people realized, de Broglie realized, Madelung realized 1926, that the wave function in quantum mechanics can be written in terms of polar coordinates. So the R here is the amplitude of a field, where the S is the phase. And so this is just mathematically allowed, if you like. And then once you do that, then you put it into the Schrödinger equation that I showed earlier. And then what you do is that you then get real part of an equation with, it's a real mathematical real. The other one will include the complex numbers. From the other one, you can calculate the probabilities, so conservation probability. But the so-called real part then gives you something that looks very much like classical physics. There's a version of classical mechanics called Hamilton-Jacobi theory, from which you can calculate trajectories. And the equation here looks like the classical Hamilton-Jacobi equation, except that there's an extra term Q, which has the dimensions of energy. And then this is, therefore, it's like a potential energy, and you call it the quantum potential. V is the classical potential. It would be like the electromagnetic potential there. And so here, what you get then is that, so we get this picture that, I mean, it's one way of thinking about it is that the difference with whenever this Q is negligible, close to zero, we get classical physics. But in situations when it's not, when it's strong, then it will influence the particle. And we are looking at the two-slit experiment here again. So again, here the particles are coming from the left, and these are possible trajectories. So depending on where the particle enter, it will then follow one of the trajectories and then end up to the screen. And now if this was Newtonian physics, they would be just straight lines. So it would be the two piles that I showed with the little bullets. But because we are now in a situation where usually you do the two-slit experiment, so it's very cold, it's like absolute zero. The circumstances are such that, you know, this quantum potential can be large. And so now we don't get straight lines, we get these funny looking trajectories, or somehow undulating. And you see now, so why do we have these trajectories? Well, here's the quantum potential on the right. And in this picture, the particles are coming from this hole towards you. And in physics, when you have a potential, you can think of it as if it were a mountain. And it means that if a particle comes from a hole here, to go up here, it would need to have a lot of energy, okay? And we can see that they don't go, we look at this, now we look from the top, when the particles come, they don't go to this area here where this the mountain is very high. They don't have that kind of energy. They're lazy. They like to go here where this landscape is very flat, and you can see it here. And again, with these things that go down here, there are similarly areas which they avoid. It's an idealization, so actually it goes to infinity. So if a particle falls into this hole, it will come back to the other side. It will spend no time here in the hole of, what do you call it? It's not a valley, I don't know the English, but you know what I mean here. So that now you can see then that if you look at this picture, now we actually see here that we get interference fringes. So we get areas where the particles don't go and some where they do go. And in this sense, we could say that this the Bohm theory provides, and the quantum potential provides, a nice explanation of the two-slit experiment. And that's one of its advantages. You can say that each interpretation of quantum mechanics will have some advantages and some disadvantages. And I won't go into all the details. The Bohm theory, you know, people have issues with the Bohm theory as well, but this is definitely one of the nice things that what at least one gets this and explanation. And now the thing is that one could of course just say, okay, that's it, there's nothing, we've done it, let's stop there. But Bohm himself felt, he of course had this holistic overall world picture and a kind of process view. He was interested in the mind and consciousness, as we heard. And so he actually then suggested that this pilot wave interpretation would imply some radically new ideas about the nature of quantum mechanical processes. And in particular, it would propose that a new type of holistic active information plays a key role at the quantum level. And so and again, we could say that this would include, if so, this would involve a radical change in what we mean by physics and the physical, and thus opening up new ways of tackling the traditional mind-matter problem. So this is again what I've been working on. I mean, first I interact with David Bohm on this in the late 80s and early 90s, and so but then I also did my own PhD in 1992, and then some other subsequent work. But Bohm himself suggested, first of all, that now we could say that information can be seen as a new fundamental category in our metaphysics, if you like. And I will tell you a bit more about what kind of information. And Bohm himself suggested that this new kind of quantum information would connect the physical and mental domains. Okay. So let's look at this quantum potential. Remember, I told you that this quantum potential is an energy. It has a dimension of potential energy. And so you see, with classical fields or classical waves, the energy depends on the amplitude of the field or the wave, the size, if you like, the size of the wave. So for example, the size of a water wave determines the effect the wave has on a floating object. So if you would have a rubber duck on a very calm pond and you want to make it move, you make big waves, and then the energy will be transmitted. If you make very small waves, not many, and even if you make very quickly those waves, it doesn't matter. But with the quantum potential, the strange thing here is that this potential Q here, it only depends on the form or shape of the field, not on its side or amplitude R. You see, one thing is here that the R here is both in the denominator and numerator, so it cancels out. So you could multiply R by 1,000, but then you have to multiply both here and here, and you are allowed mathematically, you are able to cross them out. So here, if you like, the size doesn't matter in this situation, and so what does it depend on? Again, here we say that this quantity h is a Planck's constant, and then m is the mass, which again we think of here as constant. So it only depends on this second spatial derivative of this function, this amplitude r, and what the second spatial derivative is interested is it's the curvature of this of the function, and therefore in that sense one says that it only this. So we have something quite strange in physics. We have an energy that only depends on the form of a field, and so then the next thing to say is that the quantum field is not pushing and pulling the particle mechanically like a water wave. Rather, the quantum field literally puts form into or informs the particle to behave in a certain way. And now what we have to say is that in this model, the electron is moving under its own energy that is being informed by the form of this quantum field. And this would then be an instance of a general feature of active information that we see operating at many levels of nature, where this basic idea is that the form carrying very little energy enters a greater energy, and as a result, the form of the greater energy becomes the same as that of the smaller one. And you see, this may be easy to see in artificial devices. So if you have a ship on autopilot and it's guided by radar waves, those radar waves are not pushing and pulling the ship. It's rather the form of the waves, which reflects the form of the environment, is taken up by the autopilot device and is used to direct the ship. Okay. And you see, analogously, the quantum field contains information about the environmental particle. For example, whether one or two slits are open. And this information determines the movement of the particle along with the classical forces. And you see, it looks like the macro environment informs the tiny quantum object in some direct immediate way. And what one means by that you see here, for example, in this experimental situation, these slits can be macroscopic in this whole system. The whole environment can be macroscopic in size. And whether or not you have one or two slits open, it will have a profound different effect on this quantum potential. So the electron, which is a very tiny object, is somehow aware, if you like, at least metaphorically, aware of the entire context, entire experimental context, which is in the end a macroscopic, it can be like a macroscopic environment. And you can put things here like magnetic flux lines, and they will all influence this quantum potential. So we have something in that sense rather interesting going on here. That again, that if we ask what kind of information this is, then it has this peculiar property. So it's like the way we think about it here. It's not as if there's some something that would be mediating the environment and between the environment, the particle, over and above this information. So it's enabling this. Of course, it's easy to find other examples of active information. Of course, computers would be a good one. But then people would complain, well, you're only giving these artificial things. But I think it's fair to say that in biology, it's quite common to say that the DNA molecule is guiding protein construction through the RNA, that is really, say that the DNA is really, it's like a code or language, and that is information, again, for the cell. It's not information for us. And there are, even if you study how the immune system works, there's a lot of different kinds of information. We use the concept of information to understand what's going on with viruses and those whole processes. So this seems to, something like this seems to be going on at higher levels. But of course, then there's also, there's a lot of information for us human beings. I mean, our senses give us, of course, information from the environment. When we are reading a map, we there typically we want to go from A to B. If it's a big city, maybe usually even a few possibilities arise, and we then decide which one to take, and that information is information for us. So and this goes back, you see, already. This is like 40 years ago when they published this. What the Bohm and Hiley write there is that this kind of active information ought to be acknowledged as a fundamental, or perhaps the fundamental category of physics. Why? Well, because with it you can explain all of these quantum effects, like the two-slit experiment. And so, but then they acknowledge that, and then they claim that this notion is far more subtle and dynamic than any others that have hitherto been supposed to be fundamental in physics. And of course, now one should say that their idea has not, it has not become a mainstream. I mean, there are today a lot of philosophers who like the so-called Bohmian mechanics, but in that particular version of this pilot wave theory, they don't think that this quantum potential is so important. They don't want to go and consider this active information. I think they're looking for somehow simpler, more sober, and perhaps a more sterile picture. And so in some ways, if these are the Bohmians that are known today, then maybe David Bohm is like the worst heretic of the Bohmians, because he was actually interested to look at these more, in some ways, exotic, but also philosophically richer possibilities that his theory opened up. Anyway, but this is somehow, there's kind of a sociology here, and it's interesting why. I mean, there are some people like physicists like Peter Holland who do acknowledge that this is a good, useful metaphor, at least a useful way of thinking about it, this information potential. Of course, Peter Holland did his PhD with Bohm and Hiley, but he's also one of the quite a respected physicist. And there are a number of other people who have considered this, but it's definitely not mainstream. So I should sort of warn you that if you go and talk to people about this, then you may get an incredulous stare or puzzlement at what are you talking about. But anyway, there is the literature, so you can go and look at the like the papers of Bohm and Hailey, if you're interested in this. Now, just a little thing about Shannon information versus active information. So you see, with Shannon information, we typically think about the people sending information to each other, and we quantify that information in terms of, the more surprised I get when I get signal, the more information there was. So it's kind of strongly relativized to what I already know. So if I already know the result of the football game or soccer game, I get the information about the result. Well, it's known, I already knew it, right? And but with the active information, Bohm claimed that it's not essentially related to our knowledge or lack of it, because it's information that's relevant to determining the movement of the electron itself. It's information for the electron. And it's a little bit like what the philosopher Dretske used to call information as an objective commodity. Okay. So anyway, so now this is a little bit about the physics. Now I move on to conclude to talk a bit more about this mind-body problem, and I say also a little bit about consciousness. So okay, so we've seen that Bohm proposed this kind of causal and also interactionist scheme for quantum theory, the pilot wave theory, so to repeat, the electron is a particle, which is accompanied by this field, and the pilot wave would guide or act on the particle via this quantum potential. And of course, we could say there's a very suggestive analogy that just as the pilot wave guides the particle, so mental states guide the physical body. That there's this sort of a analogy. And as we saw, that Bohm argued that the pilot waves are literally informing the energy of the particle. So you could say that already at the quantum level, we have entities which have two aspects, a thought-like wave guiding a rock-like particle. Again, talking sort of metaphorically here, but I think maybe you get the idea. And again, you see, so what we can say is that these pilot waves carry information about the environment of the particle. For example, slits is the one or two slits open. Information is carried by the pilot waves is information for the electron, it's not for us. We saw the analogy that these radio waves, just like the radio waves, carry information about the environment of the ship and inform the energy of the ship. And again, it's for the ship, not for us. We saw the information, I mentioned DNA molecule, and even in the case that when we are reading a map, then that's a information. As we could call this objective and active information. It's objective in the sense that it exists independently of human mind. Information is something that exists in the world and it can make things happen. So there's no need for us. But of course, we are part of the same game, if you like, the same process. So in some cases, of course, we are also the receivers and senders of this kind of information. And so, okay, so just to repeat that information is objective in this sense, and it typically makes things happen that is active. And you see, now we get to this mind and matter business, and the way Bohm himself tried to do it, he first started looking at mental processes, and he would say that in our mental processes, it's typical that we can make a meta-mental step. So instead of thinking about objects, we can also think about our thinking, and this can be in an extending hierarchy. So we could say that there are hierarchically organized levels of information in the human mind. But then what Bohm also said, that it's actually natural to extend the pilot wave theory. What about, he could say, so what about matter? What about this quantum information? Okay, so he would claim that not only does the pilot wave guide a particle, there can also be a super pilot wave guiding the first order wave, and so on in an extendable hierarchy. And so now we have two hierarchies of levels of information, one for mind and one for matter. And then in this article, Bohm suggested that there's actually, so we have just one hierarchy. And here's a quotation from Bohm where he writes that which we experience as mind in its movement through various levels of subtlety will in a natural way ultimately move the body by reaching the level of the quantum potential and of the dance of the particles. There's no unbridgeable gap of barrier between any of these levels. Rather, at each stage, some kind of information is the bridge. And this would imply that quantum potential acting on atomic particles represents only one stage in the process. So here you can see that, and this was, of course, quite late in his career. I think he first wrote like 1986, something like that, and then developed some of these ideas. But you see, of course, here we are saying that it's not merely a metaphor, but we actually literally think that when I move my hand, then somehow the information in my thought that I want to move my hand is going down to hierarchy all the way to the quantum potential, where maybe it could be in the synapses, in the microtubules, as some people suggest. And then this will be amplified, and then the hand will move. So somehow this information is really playing a key role in these, what we call psychosomatic processes. Whereas you see, in usual philosophy of mind, it's a puzzle. Well, there may be mental properties may exist, but there's no way they could influence the physics. Whereas here we are saying it's the fact that this matter can respond to information is there to explain that it can respond to our thoughts, information in our thoughts. And so, so one might ask whether active information is a kind of a bridge over these troubled philosophical waters. And so this is in a way just to say that we have this hierarchy of levels ranging from what manifest to subtle, and there's no unbridgeable gap or barrier between any of these levels, because at each stage some kind of information is the bridge. And so, but anyway, I'll make it a bit shorter here, just to show that this is another. He liked other term, so he had also this notion of soma significance, where typically somatic or material things carry meaning, which is then processed to higher levels. This could be in the brain, different levels of subtlety. Like when we are reading a text, the meaning will be carried to these higher levels. Once we understand it, interpret it, then there will be this, what he called the signosomatic process of going towards somatic. So you could have your perception action cycle in these terms, where these in terms of meaning and information. But I'm not going into these concepts in this talk. I just show this picture so you get a sense of how we are thinking about these levels. And so now I think if you read Bohm, so he didn't emphasize the interactionist character of this active information, or what he called the soma significance scheme. I mean, sometimes it's clear that he wants to have that. He had this other scheme called the implicate order, where he said things like mind and body are correlated projections from a multidimensional reality, this would be a kind of dual aspect monist view, where any interaction between mind and body would go via this multidimensional ground and not via levels such as in this scheme, active information and soma significance scheme, if you like the pilot wave scheme. And this, of course, you might be puzzled, what's this multidimensionality? Well, this has to do with the thing that in quantum mechanics, even if you have two particles that are entangled, their wave function lives in a 6-dimensional space. And if you would have 3 particles, you always have to add 3 dimensions to your space. So actually, in quantum mechanics, the space in which this wave function lives is a multidimensional 3n-dimensional space, where n is the number of objects. And so at one stage, Bohm was playing with this idea. But then again, and then now you can then think that mind and consciousness and matter are some kind of projections from this higher dimensional ground. But I've been always also attracted to, if you like, somewhat simpler and introduction reading of Bohm. And here, I'm coming to toward the end, that in this pilot wave framework, it's possible to think of the relation of mind and body as a kind of interaction. Because just as we say that the pilot wave acts on atomic particles, we can say that a given mental state can act on lower level mental states. These can act downwards all the way to the particles or fields in the brain. And it's not an interaction between separate substances, it's rather interaction between subtle mental levels and more manifest physical levels, as I've already said in the beginning. And so Bohm himself, he liked this kind of holistic term participation to describe the relation between the levels. But we might also call this view interactionist monism, because it's interactionist because the subtle levels can act on the manifest and vice versa. It's monism because these levels are similar in that each level has both a physical and a mental aspect. Even the quantum level has a primitive mind-like aspect, because information is information carried by a pilot wave. I mean, Bohm himself called these primitive mind-like qualities. So this would be what people call pan-protopsychism. It's not panpsychism in the full sense, but it's still like pan-protopsychism. And then it's dual aspect monism, because we are assuming that everything, even elementary particles, have both a mental and a physical aspect. They are not two substances. They're not two substances, they're manifest and subtle levels of the same substance or energy. And so actually I will skip some of these things, maybe if we get into discussion. We have these, let me see what I have here. Yes, so you see, we could ask whether Bohm's approach help us to understand how consciousness arises. And you see now, here is just a list of theories in current consciousness studies. To go deeply into this would be another talk, but I will just sort of mention that this, in the Bohmians, one could make use of these high order theories, because you remember there's the hierarchy of levels. There's the so-called global workspace theory, which might fit with this quantum field for the many-body system. Some of you may know there's this integrated information theory where this Bohm's active information could be an example of. There are a couple of other ideas. There's a Jack Sarfati had an idea that consciousness would arise. That I've pretty much been focusing the way the pilot wave influences the particle, but in physics, it's quite natural to say that if A influences B, then B acts back on A. And Jack Sarfati suggested that consciousness arises when the particles act back on this quantum information field, which is kind of an interesting idea. Of course, then we could, Penrose and Hameroff have this theory of consciousness about having to do with the collapses, and one could add this idea of active information there as well. But these are schematic suggestions. I would say that the advantage of the Bohm approach here is that we're extending a new notion to the quantum level. We claim there exists a primitive mind-like pole even at the quantum level. So we do not ask how can a purely physical system such as the brain give rise to conscious experience, which is the David Chalmers heart problem. We ask how can a system where each level has a physical and a mental or informational aspect give rise to conscious experience. And I think I'll end over there as I'm pretty much talked for 1 hour. So thank you very much.
All right, thank you, Paavo. So Michael, are you there? Or should I look at the questions? Who's gonna?
Yes, I was just thrown out of my internet for about 20 minutes, so I just logged in. But Alex, can you see the questions? Otherwise I can read
I
them.
see the questions for, okay, I guess this is a mix of questions. Some of these are from Chris's talk. And then I can't tell where the new ones start.
Okay, if you want, I can read the questions. There are 3 questions right now.
Okay, go ahead, please.
And I think, Paavo, you should be able to see them too. So the first one is by Heather Mahadi. So she's asking, can you share more about how your understanding evolved to this current model, distinct from your earlier work on quantum analogies and the process of thought?
Can you say that again?
Yeah. Can you share more about how your understanding evolved to this current model and how it's distinct from your earlier work on quantum analogies and the process of thought?
Yeah, okay. That's interesting. In some ways, they're kind of complementarity. So complementary because this work on the analogies, that's an idea that in a way it goes back to Niels Bohr and then David Bohm in 1951. So I think people there just, people felt that these things are, quantum mechanics and thought are quite analogous. And then they were looking at the so-called usual or standard quantum mechanics. So it's things like the uncertainty principle for thought, certain aspects of holism, and also something about there could be two levels of thinking, like more quantum-like process of thinking, and then a classical, so ordinary, if you like, ordinary thinking, and so it's not. I don't see a direct link or development from that to this pilot wave theory. I guess it's yet another analogy, because then here in the pilot wave we are saying that just as the pilot wave is guiding the particle, our thoughts are guiding the body. So it starts as an analogy, but then we might explain the analogy in terms of, like what Bohm was suggesting, that when mental states influence the body, it actually goes literally through this quantum potential in the brain. And that is, of course, very speculative. But it's kind of similar to what Penrose and Hameroff are proposing in their own model. But I don't know if I have much more to say about that.
Okay. The next question is by a novice, like is asking. She's a complete novice when it comes to quantum physics, so it may be a complete misunderstanding of the information concept, but she's wondering if there's any analogy from recent advances in the field of epigenetics, which seems to indicate that the experience of trauma as a mental psychological experience can be communicated at the level of DNA and cause a physical change that is transmitted between generations.
Very good question, and I think you could definitely try to do that. It would be very consistent with this whole idea of this hierarchical scheme, because here you could say that if we think that there's a hierarchy of levels, and typically all my stress, I might kind of talk about information, but of course we could talk about feelings, emotions, the whole, everything we experience in the mind, that this could act psychosomatically. Bohm himself liked the word signosomatic. And he liked to give examples, like if you are walking in the dark night and you see a suspicious shadow, and if you interpret that as the assailant, this can have a danger, right? This can have a profound influence on your body. You get the adrenaline, you get a very powerful reaction. A moment later, you say, "Oh, it was nothing but a shadow of a branch," and then you start calming down. And I think that was for Bohm this kind of paradigmatic example of the way the mind works. And the key thing here is meaning, in the sense it's not just active information, it's also what this information means. which then depends on the context, the way we decode or interpret the meaning. And of course, the general principle is that our physiological state is very dependent on what things mean to us at any given moment. And so although, I mean, there's no detailed mechanism here or no detailed description of how this could relate to epigenetics, I think in the spirit of this framework is such that it would be very natural to explore those kinds of connections, and I guess it would be to study these. Of course, people are studying these things, but it might be the case that in the Bohmian scheme might inspire even better work in this area, because then you would have this notion of active information. I don't know if people in epigenetics are using anything like that. I'm reading this book called Siddhartha Mukherjee called The Song of the Cell, where he's describing the way the immune system works. And I think there's a lot about information there. But of course, it's kind of implicit. I mean, he doesn't make it into a theme as like the way we are thematizing active information in the Bohmian framework. But I think it would be quite natural to do that, at least for the immune system.
Yeah, thank you. Then the next question, Yves Caudano is asking, the De Bohm interpretation offers to some extent an elegant approach to the two-slit experiment and others, where particles follow definite trajectories in 3D space. However, the pilot wave propagates in a more abstract setting than the standard 3D space, namely configuration space, to which I think you allude when discussing in terms of quantum fields. How do you view the physical nature, the ontology of the pilot wave, which, if I understand correctly, seems to be responsible for the information transfer required by the active information scheme you discussed? How does its nature affect your approach?
That's a very that's a very good question, and you see, one aspect here is that the pilot wave theory, when Bohm proposed it in 1952, it's a non-local theory. So there, it looks like as if you have two spatially separated systems, like in this. First you have these two entangled the particles that have been together and they're separated, they're entangled, and you do something to particle A, it seems that this will affect faster than light the outcomes of the if you do the experiments on location B. There are many different stories and versions about this, but I think for many physicists would acknowledge that there's some sort of non-locality in quantum mechanics. And of course, now the Bohm's 52 theory has this very explicitly this non-locality. And I guess the way it arises is because for two particles, this wave function lives in a 6-dimensional configuration space, and which makes possible this. But of course, the trouble is then you have to ask, well, if we say there's so what is this field? It cannot, for a single particle, the configuration space looks like our 3D space. So for a single particle, the wave is like a water wave, if you like. But for two entangled particles, the wave is already a it lives in the 6-dimensional space. And one thing that Bohm suggested is he actually tried to make, this looks like a weakness, he was trying to make into a strength. He was saying, well, this is an additional argument why we have to look at this wave function as the field of information. Because with the notion of information, it's very natural to say that we have many dimensions, that like in a computer memory, you can code, you need independent dimensions where you are coding this information. But of course, now the question is, so what is carrying this information? in typical, whenever we have information in other contexts, there's always some medium that's carrying it. Now, what is this thing that is carrying this quantum active information? And Bohm and Hiley mentioned this at the 1987 article, and they just say, well, it's some particles or fields that we haven't yet discovered. So they leave that open. They just we don't know where it is. But of course, if we accept the non-locality, or if we assume that there's real non-locality there, the way I understand it, that somehow, like in this case of two particles, somehow the six-dimensional information has to be present for both particles in a non-local way. So these are very difficult to understand, and I think the you see, in the philosophical discussion, there's been, maybe the person who asked the question knows about this, but there's a thing called wave function realism. And this is a view which thinks that the wave function is all there is, or the wave function is somehow fundamental ontologically. And if typically what we have, if you think of the wave function of the universe, then it lives in this very multidimensional space. So somehow they feel that the fundamental reality is this multidimensional. It's like this configuration space. And then now we have to explain why does it look to us that there's just this three-dimensional space. And this is a bit like what Bohm proposed in his implicate order framework. But for Bohm, the way he did it there, he said, yes, we have this, what he calls this multidimensional implicate order, but out of this implicate order unfolds the explicate order that we see in the usual familiar world of three-dimensional world of space and time. And so I think he never wanted to postulate that. I think he had a different way of looking at it, maybe a bit more sober or more ordinary way of looking at this whole thing. But I think it's still an unsolved problem in quantum mechanics, or at least in the philosophy of quantum mechanics. I don't know if the physicists worry about these things. I think they don't worry as long as they can do the experiments, but I think philosophers do worry. And so, for example, Alice Sene wrote a book about this wave function realism, and then Tim Mollin made a very critical review of it. And so as far as I can see, the question hasn't been resolved. I could finally say that in the pilot wave model, the way we think about it is that the way I think, and also the way Bohm and Hiley write about it, they would say that with the two particles, if they're entangled, then they have this six-dimensional wave function, which is then developing it lives in this configuration space, or what they call the implicate order. I think it's governed by Green's function. So you have this movement of the wave function in this implicate order, and the particles in tree space express the meaning of that information. So we have two processes. We have this dynamics at the level of the implicate order, and then we have the movement of particles in the explicate order, and this is what we have to, or if you like, this is what quantum mechanics is all about.
Okay. So this is all in terms of questions currently from the audience. If there's questions from the panelists.
I have a question.
Yeah.
Quickly. So I have here Harald Atmanspacher's new book with Dean Rickles, Dual Aspect Monism and the Deep Structure of Meaning. And he was at the camp last year. And in this book, he talks about three different approaches to dual aspect thinking. One is Pauli and Jung, the second is Eddington and Wheeler, and the third is Bohm and Hiley. And I'm wondering, so there's differences among those three theories. They're all under the family of dual aspect. I'm wondering, how much do the details of those differences matter for anybody except the specialist philosopher? Or can we get by with or consumers, can consumers of this stuff get by with the broader idea of dual aspect monism, or do the details really matter, do you think, for applying these things to social science?
But it's a very good question. It's kind of probably not, if one thinks of the dual aspects as they're just aspects, that they don't influence each other. And I think in the case of Atmanspacher, I don't know if he sometimes discusses what he calls extraordinary experiences, and then maybe he sees some sort, I don't know how he discusses these influences. Mm-hmm. But I guess I may be a little bit heretic within the dual aspect camp, because I somehow feel that this standard dual aspect to me seems too static. We just say that the mental and the physical are two aspects, but somehow we are not talking about these dynamics between the aspects, which I think is part of my everyday experience. Is still, I feel there is a sort of a, yes, I may say that there's a unity, but also, these seem very, like Descartes. In some ways, I feel Descartes was also, on the right track. Of course, although he's criticized that conscious experience is very different from my body, and yet they are intimately related. And so somehow to discuss this what I call the two-way traffic is a challenge. And I think Bohm himself he was kind of ambiguous, that part of Bohm's work seems very much, he's just think about these projections from this common ground. So we get these aspects that are being projected in a correlated way. Whereas in these other schemes, like this pilot wave scheme, which he talked about in terms of some significance, there's more that we're interested in this process. Like, I mean, simple thing, I'm reading a newspaper and somehow there's a process going toward the mental, I understand it, then it comes back to the physical. And I'm kind of, I guess it's my heretic dual aspect monism likes to have this bit more also of this interactionist aspect, although the interaction may be a bad word because it's simultaneously going from the subtle to the manifest. It's two ways all the time, but I would still like to capture this kind of dynamic, that these aspects kind of depend on they influence each other and they depend on each other, and that's somehow what we also have to understand. So that, as I said, that there's what I see as a danger of dual aspect is that it's just a little bit too static.
Okay. We can't hear you, Michael.
I know, sorry. Yeah, there's Andrei Krenikov just posted a question. So he's saying the old question of whether quantum mechanics and Bohmian mechanics have the same experimental predictions is discussed again for detection times distribution. What is your position? Do you think that one can expect in future to find real experimental deviations from quantum mechanics predicted by Bohmian mechanics?
That's an interesting question. Of course, I'm not a specialist on the physics side, but of course I follow the literature. I think even when Bohm published his first 1952 papers, he already there discusses some possible areas where he could get predict different results from the usual quantum mechanics. Maybe they were like in the very high energies or very, very short distances. And I guess none of those hopes have kind of come true or realized themselves. And I don't know about those others. I think of course, Basil Hiley and the team, they are doing these experiments in University of College related to weak measurements, and also exploring some of these, if you like, the new possibilities that the Bohm theory gives for experimental work. they also I think there was this Bohm Centennial Conference in 2017, and the proceedings are published in the Entropy. I know Andre was there himself. I think in some of those papers, Hailey and Van Reeth and some of the others, they describe some of these experiments, which at the moment, unfortunately, they haven't been able to complete all of them yet. I think the COVID came in a bad moment, and they have difficulties of getting setting everything, finishing everything there. But I don't know even there whether they would claim to have an experiment which would be predict, if you like, or whether whether you could come up with the different predictions from the usual. So that's, of course, would be exciting. I guess in the Girardi, Rimini, Weber spontaneous collapse or objective collapse theories, maybe some of those would actually make different predictions. But I think Andre probably can answer that question better than I. But it's a fascinating question. I think as a philosopher, of course, this is very interesting because you can say it's all like that. Why did Bohm in his 52 paper, why did he add these things about different predictions, new predictions, different from the usual? Well, maybe partly because then otherwise people would say, well, what are you doing? You're just giving us an other model, but you're not making any new predictions. So why should we give attention to your theory? And then he would only have to say, well, it's more beautiful or gives a better explanation or this or that. But of course, science becomes more exciting when the new hypothesis actually makes new predictions, and then we can go and test. I mean, this is sort of thing that Popper loved, that we should make these bold hypotheses that make these predictions, and then you go and test. And so, but you see, but on the other hand, the reason why the Bohm theory has survived, like, from 52, what is it now? 24, 70 years. One of the reasons why it probably has survived is because it does give exactly the same predictions as standard quantum mechanics. And then we can just argue which theory is more elegant. Or, we can go to those more subjective criteria of evaluation. And so it's a very difficult game, I would say. You see, because if somebody comes with an exciting new theory which gives very different predictions from quantum mechanics, probably some people say, well, we get, I guess it's more with relativity, but you get these alternative pictures. And the challenge is you have to give all the same predictions as quantum mechanics and then some extra ones. So how do you do that? I mean, maybe Andre knows.
Joyce has her hand up.
Yeah, I just thank you so much for both Paavo and Chris, if Chris still is there. So those are so excellent, and I learned so much. But I also want to just have quick comments, maybe especially for young scholars, young students out there in the audience, because you're entering a very interesting field and very intellectually deep but diverse field, and maybe we can do something like Chris was suggesting earlier, like just learn everything you're interested in. But I think everyone have practical career and kind of development requirements and demands right now. So I just want to maybe also a little introduction about how we organize the workshop. Like we have a lot of views, and on Thursday, like in the afternoon especially, we do a very, very tutorial, like very simple, at least from one kind of research field, like cognitive decision making field and choice behavioral field. See how we don't have answer for everything, but there are reasons for why we need some kind of new theory perspective. And yeah, welcome. So kind of advertisement, but also a showcase and tutorial to see how like one part of field, one small research program is trying to do this. And And there are a lot of questions and a lot of questions we don't have answer, and a lot of things. We're just scratching the surface of the possibilities and potential here. But I think just a follow up, actually, Professor Andrew Krinicus and actually Professor Alex Wang's question here, and like how we empirically show, yeah, this is useful beyond being so beautiful and elegant. So, but anyway, we'll come to that later tutorial.
Okay, in the meantime, Andre posted a comment. Sorry, I got disconnected again, so my internet is a bit stable. And he says, recently in Växjö in Sweden, we have the big debate with cubists on intersubjectivity in quantum mechanics. It was related to new results in measurement theory obtained by Masano Ozawa. This theorem is in favor of realism of quantum observables. This is really a new supporting argument for the realism in quantum mechanics. And then Andre is posting a reference on the archive. Yeah, I just wanted to mention this.
Yeah. No, it's excellent. No, it's interesting. It's of course Chris Hooks is he has this cubism, which is also a very interesting view. But I personally have a little bit. I still have this kind of realist preference, at least. Although the realism we get in quantum mechanics is typically, you could say, any reality we get from quantum, it will be context dependent, like we saw, and also it will be probably dependent on deeper levels. I mean, this is what we assume, that, because of course in physics it has been the story that we study a certain level, but then it's possible to go deeper, and usually a given level depends on the lower level, but it can be also, of course, vice versa, that you can have this kind of level difference. So my view is that we can have a realist view, but it's not going to be the same as in classical physics. And I suppose the quantum in that, coming back to social sciences, that in some ways I think there are interesting analogies between the kind of quantum reality that we can get from the Bohmian picture and other pictures, and the way the social reality seems to be. And of course, this is something that Alex Wendt has discussed in his book. But I think that is still it's a theme worth exploring. And then we have to also be careful not to get too much lost in the nitty-gritty of this quantum mechanics, all these quantum ideas, because somehow, and to remember that probably every quantum approach has its beauty and value, but also some problems, because people are not agreeing. Okay, and that's if you come from the social sciences, so somehow you need this big bucket of salt. So you always have to read everything with the grain of salt, and somehow just try to build your own picture. And one trouble, of course, is that not everybody in the field is very humble. So sometimes they want to say that they have the truth, or somehow this is the way it is. And whereas I think the more honest approach is to acknowledge that, of course, we know a lot. People agree about great many things about quantum mechanics, but there are also disagreements about very important questions. And in that sense, the situation is genuinely open. And somehow what we have, if I'm a social scientist, I still have to distill some essential principles or ideas. Most people might agree that there's some kind of holism in this quantum phenomena. Causation is interesting. It's not necessarily absolute indeterminism, but it's definitely a more interesting picture of causation that we get in classical physics. And there might be a new, like what I was talking about, the way information might come into it. But it's a big question, what kind of information and what is meaning? Does meaning come into it in some way? And is it the kind of meaning that we encounter in the social sciences? And there are many there are many interesting possibilities, but there's really much work to be done to try to somehow see which concepts in the end will turn out to be and which metaphors will be useful for the social science.